Okay, this is note 7, infinite limits and limits at infinity. So here we're going to compare and contrast the behavior of functions as they approach infinity, as well as the functions that tend toward infinity in certain circumstances. So in this first one, we're going to look at the functions f of x and g of x. So in this first part here, we have the limit as x approaches 4 from the left and as x approaches 4 from the right. So here is 4. Notice that on 4 we have a vertical asymptote. So as it's approaching 4 from the left, that's this function, and then 4 from the right is this function, we notice that one is going towards positive infinity and the other is going towards negative infinity. This one is looking at the function g of x, so it's this one down here, and it's looking at as x approaches 1. So here's 1 on either side. Notice again we see another vertical asymptote, and on the left side it's going towards negative infinity, and on the right side it's going towards positive infinity. So our discovery is that these limits are approaching a vertical asymptote. And we see that in our formal definition that says an infinite limit is as x approaches c, the limit approaches either positive or negative infinity where there is a vertical asymptote. Okay. This next part wants us to look at the function f of x at negative infinity and positive infinity. So here's f of x. Negative infinity would be on this side and positive infinity would be on this side. So as x is approaching negative infinity and as it's approaching positive infinity, notice that there is a horizontal asymptote here. So that means that is what it's approaching on either side, and it's that horizontal asymptote at -2. Okay. Now looking at g of x, so this one here, looking at the left, okay, and the right, so as we approach positive and negative infinity, notice that as we're approaching negative infinity, the function is approaching negative infinity, and as the function is approaching positive infinity, we're approaching positive infinity. Okay. And you'll also notice that around those points, we see a slant asymptote. Okay, so in this part, we see a horizontal. In this part, we see a slant asymptote. So looking at our formal definition, a limit at infinity is the same as saying as x approaches positive or negative infinity, the limit will approach a y value or be unbounded. So a negative infinity or positive infinity. Okay. So again, this is showing our horizontal asymptote. In pre-calc, you learned about rational functions. When we factor and cancel from a rational function, then we know a whole occurred. If we factor and cannot cancel from the denominator, then we know a vertical asymptote occurred. So using the previous equations, we're going to find the one-sided limits of each of them. So notice this is the limit as x approaches 4 from the left, and then next to it is 4 from the right. Okay, so first we're going to factor the numerator. We're going to take out a -2 GCF, and we're left with x plus 3 times x minus 2. And then factoring the denominator, we have x minus 4 over x minus 2. Notice that our x minus 2 can cancel, which tells us that there is a whole at x equals 2. And then what we have left over is the limit as x approaches 4 from the left of negative 2x plus 3 over x minus 4. Well, if we were to plug in 4 into this, we would end up with something that is undefined. So instead, I'm going to pick a number to the left of 4, and we're just trying to see if the numerator and denominator give us a positive or negative value. So if I plug in 3, I have negative 2 times 3 plus 3 over 3 minus 4. This gives me negative 2 times 6, which is negative 12. 3 minus 4 is negative 1, which gives me a positive 12, which tells me that this limit is approaching infinity. Okay. Then I'm going to look at the same thing, but now I'm looking at the right side. So this is the limit as x approaches 4 from the right. And since I already factored in part A, I'm just going to write the factors that I had. And again, I can't plug in 4 because I'll end up with something that's undefined. So I'm going to pick a number to the right of 4, which could be 5. So negative 2 times 5 plus 3 over 5 minus 4. This top part is going to give me something that is negative. The bottom part is going to give me something that is positive. So overall, this function, this limit is approaching a negative value. So I know that it's approaching negative infinity. Part C. Again, my first step is always to see if I can factor. Looking at the numerator, I'm not able to find two numbers that multiply to 5 but add to negative 2, so it's not factorable. So what I'm going to do instead is just plug in a number to the left of 1. So I can do the limit as x approaches 1 from the left, and I can pick any number. So let's say I pick 0.5, 0, negative 0.5, any of those would be okay. So let's go ahead and make it easy on ourselves and choose 0. So if I plug in 0, you'll notice what is happening is that the only values are left over are the ones that did not have x next to it. So I'm left with 5 over negative 2, which is negative, which tells me that my limit as it approaches x from the left is going to approach negative infinity. Okay. D, I'm going to pick a number to the right of 1, so let's just pick 2. So I have 2 squared minus 2 times 2 plus 5 over 2 times 2 minus 2. Okay, on the top I have 4 minus 4, which cancels out, plus 5, so I have a positive. And then 2 times 2 is 4 minus 2, which is positive, which tells me that this is going to approach positive infinity. Okay, so in pre-calculus, we learned that if we were to plug in a value, let's call it c, so when x is equal to c, into our function, we can end up with two possible cases for a vertical asymptote. We could end up with a number over 0, which tells us vertical asymptote. Or we could get 0 over 0, which tells us, yes, there's a discontinuity, but it's not necessarily a vertical asymptote. Most likely, it's a hole. Okay. If we were to transform this into a definition used in calculus, this would be the same as saying if the limit as x approaches c from the left of f of x is equal to positive or negative infinity, or if the limit as x approaches c from the right of f of x is equal to positive or negative infinity, then x equals c is a vertical asymptote. So pretty much if we were looking at the limit from the left or the limit from the right and we see that it's unbounded, meaning it goes to infinity or negative infinity, then we know at that value, x equals c, there's going to be a vertical asymptote. Okay, so let's practice that. In example 3, it wants us to use this function to see if there's a vertical asymptote. If there is, we need to justify using our definition. Okay, so the first thing I'm going to do is factor the numerator and the denominator, and I get 2x minus 1 times x plus 5 all over x plus 5 times x minus 2. So at x plus 5, since they cancel out, this tells me that there is a hole at x equals negative 5. But we don't want to know if there's a hole. We want to know if there's a vertical asymptote. So in order to determine that, we're going to look at the denominator, and in this case we have x minus 2, and see what value would cause this to be undefined. Well, that value would be x is equal to 2. So we need to prove if the limit as x approaches 2 from the left and the limit as x approaches 2 from the right, and see if we get infinity or negative infinity to prove that it's unbounded. Well, if we plug in 2 from the left, okay, that means I could plug in 0, so I end up with negative 5 over negative 10, which is going to be positive, so that's infinity. And if I plug in 3, I'm going to get, let's see, 2 times 3 squared plus 9 times 3 minus 5 over 3 squared plus 3 times 3 minus 10. This is going to give me positive on both of them, which means this is going towards infinity. Okay. Since my limit as x approaches 2 from the left and to the right are unbounded, then I know that at x equals 2, there is a vertical asymptote. And I proved that, or I justified that, by doing the left and right-sided limits. Okay, so that's infinite limits. Now let's look at limits at infinity. Okay, in pre-calculus, you learned how to look at certain functions and determine the end behavior based off of these functions. So for example, looking at a, if I was to FOIL this out, I know that this is going to be a function of x squared. Okay, x squared is a polynomial with an even degree. And since this is as x is approaching infinity, as I plug in positive numbers that are increasing, so for example, if I plug in 1, then I plug in 100, then I plug in 1,000, I see that my numbers will also be increasing. So as x increases, f of x increases, which tells me that the limit is going to approach infinity. Okay, on part B, I notice that this is a cubic function. So this is a polynomial with odd degree and positive coefficient, the 5. Okay. And I'm plugging in a negative infinity. So if I continue to plug in negative numbers into x cubed, I'm going to result in a negative number. For example, negative 2 cubed is negative 8. And since I'm multiplying by a positive leading coefficient, I'm still going to end up with a negative number. So that means as x decreases, f of x decreases, which means that my limit is going to approach negative infinity. Okay, so these are polynomials. What if we had rationals? So for rationals, we have to first determine if there's a horizontal asymptote. And if you recall from Algebra 2 and Pre-Cal, we can determine this by looking at the degree of the numerator and the denominator. So notice that both these degrees are 2, meaning they match. Since they have the same degree, I know the horizontal asymptote is going to be the ratio of the coefficients in front. So technically this is 3 over 1, which means my limit is going to equal 3. So since my degrees are equal, this implies I have a horizontal asymptote at the ratio of coefficient. So this implies y is equal to 3. Okay. For D, the same thing. I still look at the degree of the numerator and the denominator. But notice this time that the denominator degree is greater than numerator degree. When this happens, the horizontal asymptote is going to be y equals 0. So as x approaches negative infinity, my limit is going to approach 0. Okay. Same thing here. This is taking the equations that we did on the last example and showing you in graph form. The only thing you need to do is change these ones up in order for them to match. They mixed up C and D. So A says the curve can increase without bound. So the limit as x approaches infinity is going to be infinity because this is a polynomial of x to the power of n where n is even. Okay, which means as x increases, f of x increases. Part B is a polynomial of degree n where n is odd. So in this case, we saw x cubed. So as x is decreasing, we know that f of x is going to be decreasing, so we get negative infinity. C and D showed us rational functions, which means that the curve is going to approach an asymptote. So in part D, since the degrees were different, so it was larger on the bottom than it was on the top, then this tells us that it was going to approach y equals 0, or in this case, the x-axis. Okay. And then for the other part, it says the curve can approach an asymptote at a specific y value. So this was the case where the degrees were the same, so we were able to get the exact horizontal asymptote. So in this case, it was 3 because that's where they're approaching on the graph. Okay. This next part is just some formal definitions. Okay, so everything we just talked about. If you want to go ahead and pause here and read for yourself, just know that we've talked already about all 3 of these. The only one that I would emphasize is that if you have a degree of the numerator that is greater than the degree of the denominator, then the horizontal asymptote does not exist, which means the limit does not exist. And instead of a horizontal asymptote, we have a slant asymptote. Okay. So in this part here, in the instructions, it says we are going to apply the properties of limits to evaluate each piece to find the limit at infinity and the end behavior. In order to do that, we are going to divide by the x that has the highest power in the denominator. So for example, the highest power in the denominator is 2. It's attached to that x, so we are going to divide by x squared. Every single term. So 2x squared divided by x squared minus 10x divided by x squared divided by x squared, minus 8x divided by x squared, and plus 15 divided by x squared. Then I'm going to simplify and reduce if I'm able to. So these x squareds are going to cancel out. These ones are going to be left with an x on the denominator, and then 15 over x squared can't cancel. So we're left with 2 minus 10 over x over 1 minus 8 over x plus 15 over x squared. Well, since this is as x is approaching infinity, okay, let's imagine that each of these values on the denominator where it has x are going to continuously increase. So as our denominator is increasing, we are actually getting a smaller and smaller decimal, which means if I was to take the limit of that, it would approach 0. So anything that has a x in the denominator, we know is going to approach 0 when I take the limit of it, which means I am left with 2 over 1, which is 2. So the limit as x approaches infinity of f of x is equal to 2. And we can prove that further because we know we have a horizontal asymptote at y equals 2 because our degrees on the numerator and the denominator are the same, which means we look at the leading coefficient ratio, which in this case is 2/1, which is 2. Okay, part B, we're going to do the same. We are again looking at the denominator to find the highest degree, and we see that is x squared. So I'm going to divide by x squared. So I have x divided by x squared plus 3 over x squared over x squared plus 4x over x squared plus 5 over x squared. Then I'm going to reduce, and I am left with 1 over x plus 3 over x squared over 1 plus 4 over x plus 5 over x squared. Since it's x approaching positive infinity, anything with an x on the denominator is going to approach 0, which means I am left with 0 over 1, which is equal to 0. So this tells me that the limit as x approaches infinity of f of x is equal to 0. And I can also prove that by remembering my properties of rationals and know that if my degree on the denominator is larger than my degree on the numerator, then I'm going to have a horizontal asymptote at y equals 0. Okay, part C, I have the limit as x approaches infinity, but in this case, looking at the denominator, notice that I only have my highest degree as 1, which is attached to the x. So I'm going to divide everything by x. So I have x squared divided by x minus 4x divided by x minus 3 divided by x divided by x minus 2 divided by x. Simplifying, I'm left with an x on top. This goes to 1. So this is equal to x minus 4 minus 3 over x over 1 minus 2 over x. So everything with the denominator of x on the bottom is going to go to 0. Okay. So what I'm left with is x minus 4 over 1 or x minus 4. Well, if I was to find the limit as x approaches infinity, that means as I continuously plugged in numbers that were going in the positive direction, so let's say I start with 10 and then 100, then 1,000, then 1 billion, I would notice that this would be increasing rapidly. So this tells me that my function is actually approaching infinity. And what does that tell us? That tells us that we do not have a horizontal asymptote, but instead we have a slant asymptote. And when we have a slant asymptote, we need to find that using the long division. So long division, I have x squared minus 4x minus 3 divided by x minus 2. So in long division, if you recall, you always look at the first two terms. So x goes into x squared, x times, meaning x times x will give me x squared. And then I multiply that x by everything that I'm dividing by. So this becomes x squared minus 2x. I change the signs and add down. The x squareds cancel, and I'm left with negative 2x. Bring down the negative 3. And then again, I'm looking at negative 2x. X times what will give me negative 2x? Well, that would be negative 2. So I have negative 2x plus 4. I change the sign, add down, and I am left with negative 7. Well, x cannot turn into negative 7, so that is my remainder, which means my slant asymptote is going to be y equals x minus 2. Okay, so summarizing what we just did, we noticed that when we have functions that have horizontal asymptotes, the limit as x approaches positive or negative infinity is always going to be b, where b is a real number. This says that the line y equals b is going to be a horizontal asymptote. If functions with slant asymptotes, we take the limit as x approaches positive or negative infinity. We're going to either get positive or negative infinity back, okay? Which means in order to find that slant asymptote, we have to use long division. Okay. So turning this into a formal definition for horizontal asymptote, we said if limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x equal to b, then y equals b is a horizontal asymptote. So if either side of the limit as it's approaching infinity or as it's approaching negative infinity is going to give us b, then we know we have a horizontal asymptote at y equals b. Okay, and then last part here says challenge. So what I would do is I would pause the video, try it on your own, and then unpause for the answer and then compare your work. So we're going to do the same thing we did before, where we're going to look at the highest degree in the denominator. In this case, that degree is that 2. So what we're going to divide by is the square root of x squared. Well, the square root of x squared is the same as saying the absolute value of x, because x could be positive and x could be negative. Okay? Off to the side, you'll notice that it's telling us to find as x approaches negative infinity and as x approaches positive infinity. Okay, so starting with the limit as x approaches positive infinity, I am dividing each of these terms by either the square root of x squared or the absolute value of x, since they're the same. So this is 3x divided by the absolute value of x minus 3 divided by the absolute value of x, divided by the square root of x squared divided by x squared, plus 4 divided by x squared. Notice that in the denominator, I already had that radical there, so it made more sense to just divide by what's inside of the radical versus dividing by the absolute value of x, because I want to try to cancel something out. And then the same thing for the limit as x approaches negative infinity of the same thing here. The only thing that's going to change is that absolute value of x, depending on if we are approaching positive or negative infinity. Okay, so for the positive one, these are actually going to be positive values. So we could actually just rewrite this as x, which means this is equal to, because the x's will cancel, 3 minus 3 over x divided by the square root of 1 plus 4 over x squared. And since this one is approaching negative infinity, we would actually change these absolute value bars to negative x. So then this is equal to 3x over negative x. The x's would cancel, so it would be negative 3 plus 3 over x over the square root of 1 plus 4 over x squared. Okay. Anything with an x in the denominator we know is going to approach 0. So this goes to 0, so does this. So that means for the limit as x approaches infinity of g of x, we get 3 over the square root of 1, which is 3. And then the limit as x approaches negative infinity of g of x, we get negative 3 over the square root of 1, which is negative 3.